Well,
All right, that looks good, Ben. It's coming through.
Let me try also. Okay.
Looks good, Patrick. Came through.
And Woo, it looks like you might have clicked that start webinar button. So there are people starting to join now.
Yeah, I mean, because it's only 2 minutes to go. So now, like, we have 4 attendees. So Ethan, if Lucas is not here on time, we'll just go for the schedule, and then later if Lucas join, then maybe he'll be the last. Okay.
Ooh, he
Let
is
me see.
here.
Lucas is here. Let me see. Promote to the panelist. Okay.
Yeah, you should have gotten an email, Lucas, from
Yeah,
you all
now-
with a direct link as a panelist. There you go.
Yeah, but now I allowed him to the
Perfect.
panelist.
Okay,
That's
yeah,
why I
sorry.
think-
I must have clicked on the wrong Zoom link.
No, it's okay. No, that's why I wanted to click the start webinar. Otherwise, maybe you are nowhere. That is good. So
You're here.
now, yeah, Catherine, go ahead.
Oh, I was just gonna say, yeah, he made it. You're here. That's all that mattered, right? So it's all good. We're good. Glad you can make it.
So Catherine, as you recommended, could you guys maybe a little bit introduce as a judge?
Sure, absolutely. Happy to do that. Catherine Hansen. I am currently with Minnesota IT Services, partnering with the Department of Natural Resources. I do a lot of the GIS support and training for the employees at the DNR. I also have, for the last couple decades, taught at the University of Minnesota for the MGIS program, and also have been the GIS lab manager and instructor at the University of St. Thomas, and my roots back down in Mankato. So TA and teaching down there as well. So yep, I'm happy to be here. I read through the papers. I'm excited to hear your guys' presentations. Thank you. This is going to be a fun day.
Okay. Mr. Mohapatra.
Thank you. I'm Rama Mahapatra, geography at Mankato. I don't have that kind of 25, 30 years of background in Minnesota. I came in 2010 and currently I'm associate professor. I teach many GIS courses.
Okay, so first of all, thanks for you joining our graduate student paper competition. This year we have 4 students, to present their topics. My name is Wu. I'm currently Minnesota GIS Alliance Higher Education Committee Chair. So I'm in charge of the all student competition. So our moderator Ethan Larson will introduce the presenter order by first name and last name. After that, each presenter will spend 25 minutes, but 20 minutes for presentation and 5 minutes for question. But if you just attended the section, now we have 4 presenters, so we're not gonna make all our 90 minutes for the all presenters. So maybe we need to spend the extra, maybe 10 to the 20 minutes more. So if you have another section, feel free to leave this one. Otherwise, I hope you could stay and then listening to our wonderful presentation. So Ethan, could you introduce our first presenter?
All right. Hello. Our first presenter is Benjamin von Korff from Minnesota State University, Mankato. He recently graduated in the summer of this year from MNSU with a MS in data science with certificates in both GIS and database technologies. His research focus was using remote sensing and statistical analysis to monitor and forecast algal blooms. He is also a water quality specialist at the Water Resource Center at Minnesota State University, Mankato, where he monitors water quality in the Greater Blue Earth River Basin as part of the Watershed Pollutant Load Monitoring Network, known as WPL-MN. He has interests in using GIS and remote sensing along with data analysis to solve environmental problems. And he also has an MS in marine sciences from the University of North Carolina, Chapel Hill in 2011. And he also has a Bachelor of Science in Biology from U of W Madison. And the title for his presentation is Assessing and Forecasting Chlorophyll Abundances in Minnesota Lakes Using Remote Sensing and Statistical Approaches. Ben, you have the table.
Okay, I'm going to share my screen. So my presentation is on assessing and forecasting chlorophyll abundances in Minnesota lakes using remote sensing and statistical approaches. This was part of my thesis project in data science. My advisor was Guaryanic Salivia. I'm going to give a introduction with a background on harmful algal blooms. And we used two approaches for monitoring harm and forecasting algal blooms. I'll give some background on part one, using unmanned aerial vehicles or UAVs. Part two, time series forecasting. And I'll go over the research questions, move on to the methods, the results, and discussion. To start off with, harmful algal blooms can injure humans and wildlife through producing cyanotoxins. The algae on the right is a cyanobacteria called Anabana. The new name is actually Dolichospernum. And this is from a water sample in Bass Lake in Faribault County, Minnesota. They reached out to us a few years ago due to problems with algae at their lake. And we started monitoring and doing research on their lake. In addition to causing problems due to the toxins, cyanobacteria can produce harmful algal blooms can harm lake aesthetics, and their frequency is expected to increase with climate change. Despite these problems, monitoring for algae blooms is infrequent and reactionary in Minnesota, and there are challenges to monitoring them well. They can vary spatially in a lake, and they can also occur rapidly and dissipate quickly. Remote sensing is a good tool for dealing with spatial variability. If you just grab one sample in the middle of the lake, you might miss an algae bloom elsewhere. And one advantage that UAVs have over satellites is they can get below the clouds, so they can be used to collect imagery on cloudy days and collect high resolution imagery. Time series forecasting is another tool for managing algal blooms using monitoring data. We can collect monitoring data, lake conditions, data on chlorophyll, which is a measurement of algal biomass, and we can use that data to forecast whether there's likely to be a bloom in the future. But these methods can be expensive. A water quality sonde to measure water quality conditions to use in a forecasting model can be $10,000 or greater, and some cameras that you may map algal blooms with a drone, like a hyperspectral camera, can be up to $50,000. So we're really interested, I was interested in my research in finding ways to lower the cost of monitoring for Minnesota lakes. To start off, I'll give some background on UAV remote sensing. This graph shows the chlorophyll A reflectance spectra. For water-containing algae, the thick, darker line, and for clean water, the thinner line. And you can see that algae has peaks in the green region and near infrared areas, and troughs in the blue and red areas. We can use this to map algae using band ratio algorithms. Normalized difference vegetation index is one of the most common band ratio algorithms used. It's the NIR minus red divided by NIR plus red. And it works well because algae reflects near infrared light. Another common algorithm is blue NDVI, NIR minus blue over NIR plus blue. And you can see the graph on the right, there's a positive relationship between blue normalized difference vegetation index and algae. Here, the measurement they're using is buoyant packed cell volume. So as the amount of algae increases, the BNDVI also increases, and there's a good correlation between the two. You can also use narrowband algorithms. Normalized difference chlorophyll index, NDCI, uses specific bands which target the near infrared and red region. It's more accurate than NDVI. In order to map algae using these methods with a drone, you would need at least a camera with a near infrared capabilities, or a multispectral camera or a hyperspectral camera. That could range in cost in thousands of dollars to up to 50,000. Recently, there was a publication by Shiraishi et al. In 2018, where they used an RGB algorithm to map algae. Their algorithm they called Visible Water Residence Index, VWRI. It's the green minus blue minus red divided by green plus blue plus red. And it works in theory because there's a reflectance peak in the green region when algae is present. They found a positive correlation between VWRI and chlorophyll, but this algorithm was not tested in the field using a drone or other methodology. If we were able to use this band ratio algorithm in Minnesota lakes, a simple fan forward drone, which would range in costs from $1,000 to $1,500, could be used to map algae. I'll give some background on time series forecasting. Time series forecasting methods can also range in costs. The graph on the right is from a paper by Zhao et al. 2017. They estimated the monitoring costs of doing monitoring many parameters on the left, such as meteorological, water quality parameters, electrochemical factors in many different lakes, and developing a chlorophyll forecasting model based on that. And they estimated the cost would be about $350,000 for their lakes. If only electrochemical factors are measured using a water quality sonde, like pH, dissolved oxygen, the cost decreases. And the simplest monitoring method is to use a single probe, which measures one parameter, like chlorophyll A, and a univariate forecast can be built off of that. And that they estimated the cost would be $50,000 for their program. So the fewer parameters that you are required to model for your time series forecasting model, the less your monitoring program costs. They found that their univariate forecasting method worked well in their study, and we wanted to test this in Minnesota lakes. And I was interested in seeing whether a multivariate forecast was more accurate, and if so, by how much, compared to a univariate forecast. For my forecasting methods, I used a classical approach called a RIMA, autoregressive integrated moving average. And this is parameterized by P, D, and Q. P is the autoregressive order, D is the difference order, and Q is the moving average order. I also used a machine learning approach, long short-term memory, or LSTM. Machine learning is often used for chlorophyll forecasting because machine learning is good at forecasting nonlinear processes. It suffers from being computationally intensive and being a black box approach in that I can make a model that works, but I may not understand why. The research question from my study were, first of all, how does the accuracy for chlorophyll mapping compare between an RGB algorithm, VWRI, and a near infrared band ratio algorithm, NDVI? My second question for the time series forecasting side was, can a univariate forecast perform as well as a multivariate forecast? And is a computationally intensive forecasting approach required in Minnesota lakes? I'll move on to the methods now. I used a Phantom 4 drone, and it also had a Centera NDVI modifications. So there was a second camera on the drone that could measure near infrared light. This is an example of my drone image over Bass Lake in Faribault County. The red dots are where I collected a chlorophyll sample. That was measured using a chlorophyll probe on a YSI sonde. I flew the drone over a section of the lake and stitched the imagery together using Drone Deploy, which is a cloud software. The GPS points for each of these sampling locations was taken using an Android phone, and that was due to practical budget constraints, but it was also in line with my goal of producing a methodology that could be done at low cost. I created both a stitched imagery set of the RGB imagery, as well as the false color imagery from the Centera camera, and geo-reference the two to match each other. To account for potential error in the GPS measurement, and also the potential for algae to drift between the time the sample was collected and the drone flew over that spot, we added a between a 2.5 to a 10 meter buffer around each of the sampling points. And zonal statistics as a tool was used to calculate the average chlorophyll, the average VWRI or average NDVI at that point. And VWRI and NDVI were calculated using raster calculator. Here's a picture of the Centera camera. The way that it measures NDVI is actually a little bit different. It has two channels that they actually both measure red and near infrared light. And so there is a alternative equation for NDVI that you have to add. I added coefficients in front of these bands to account for unequal differences in irradiation of the red and near infrared bands. Moving on to the time series forecasting, I used a YSI sonde that measured turbidity, specific conductivity, pH, water temperature, chlorophyll A, and ORP every 15 minutes. This was from May to October in 2019 and 2020. There was also a weather station which measured wind speed, wind direction, air temperature, rainfall, and photosynthetically active radiation. There was some missing data in our chlorophyll time series, and that data was imputed to the median. That chlorophyll data is measured using a chlorophyll probe on the YSI sonde. ARIMA was performed on the time series of chlorophyll data, and we used auto ARIMA to select PD and Q parameters. LSTM was performed in Python, and 67% of our data set was used for training and 33% for the forecasting. LSTM included both a univariate forecast and a multivariate forecast. I also tried using a wavelet transformation, which can sometimes increase the accuracy of time series forecasting. What a wavelet transform does is, you can see on the right, it splits the data set into an approximation and 3 detail sets. The forecast is then done separately on each of these sets, and the end result is added together to reconstruct the chlorophyll time series. Moving on to the results, I checked to see if there was a correlation between VWI and chlorophyll A on 4 different flights during 2020 in the fall. The graph on the left is the correlation between VWRI and chlorophyll A, and the graph on the right is NDVI. There was a positive correlation between VWRI and chlorophyll A in both cases. I used a polynomial fit for NDVI since that worked better based on the p-value and r-squareds. The r-squared was just better during this flight for NDVI. Using the regression relationship, NDVI and VWI was converted to chlorophyll A, and here are the maps from this September 14th flight. Our best model again in this case was NDVI, and you can see that there's a band of higher concentrations of chlorophyll near the shore with concentrations ranging up to 600 micrograms per liters. That's an extremely high concentration. Anywhere 50 or above is considered eutrophic in lakes in general. The VWRI model appeared to show much more spatial variability in its estimated chlorophyll concentration and showed higher extreme values with concentration ranging up to 1,000 micrograms per liter. Here's the data from September 18th. In this case, VWRI had the best correlation with an R-squared of 0.799, but there was also a good correlation between NDVI and chlorophyll A. Here are the maps of chlorophyll A during these flights. You can see that there's a band of algae on the northeastern portion of the lake. In both cases, the chlorophyll ranged from 0 to around 65 micrograms per liter. So there were generally similar results between both methods. On September 26th, there was a better correlation between chlorophyll A and NDVI than VWRI. And in this flight, it seemed that NDVI did a better job of highlighting the algae along the shore, where VWRI showed more patchiness in the map of algae. It also showed higher, more extreme values in some cases in this flight. On October 18th, VWRI had a slightly higher correlation than NDVI. And in this case, I was able to map the entire lake using 4 flights. VWRI again had generally higher concentrations with more extreme values ranging up to 283 micrograms per liter compared to a maximum of 133 for the NDVI model. When I combined all the data together from each of the 4 flights, there was still a strong correlation between NDVI and chlorophyll A, whereas VWRI, there was no longer a correlation. Moving on briefly to the time series forecasting, I'm gonna get through this quickly. In order to do a multivariate forecast, I tested if there was a correlation between the measured water quality and meteorological parameters and found that turbidity was negatively correlated to chlorophyll A, so was specific conductivity, and chlorophyll was positively correlated to water temperature in the past 60 days of precipitation. So these parameters were used in a multivariate forecasting model. The forecasting results are shown here from 2019. RMSE, root mean squared error, is used as a measurement to compare the models. The LS on the upper left, the long short-term memory multivariate forecast had an RMSE of 2.791. The blue area, or the blue line, is the forecasted section, and the black line is actual data. The univariate forecast had higher performance with an RMSE of 1.76. The wavelet LSTM, also a univariate forecast, had the worst performance, and ARIMA had the best performance, although it's worth noting that the forecast was relatively flat. This is
That's less than 3 minutes, Ben.
Thank you. This was a 10-day forecast. Here are the 2020 results. We found similar results with the best performance of ARIMA, followed by the univariate LSTM forecast. So what does this all mean? First of all, this was the first study that we are aware of to test VWRI in the field. Our results confirm the study of Shiraishi et al. 2018 for that VWRI can be used for UAV mapping of algal blooms. However, we found that NDVI significantly outperformed VWRI. There was a more consistent relationship between chlorophyll A and NDVI, which would mean that you could potentially take the drone out, collect your samples, and use that same regression relationship for your future flights. NDVI also produced less patchy results and tended to highlight algal patches better. Future work, we recommend that I would like to see testing to be done to see if narrowband methods like NDCI, normalized difference chlorophyll index, could increase the accuracy of the results. That would require a more expensive camera. Our recommendation for monitoring using UAVs in Minnesota is to use a Phantom 4 drone with a Centera modification rather than just the RGB camera of the Phantom 4. The cost would be about $3,000 for the drone plus the camera, and it would require occasional chlorophyll sampling, plus some kind of software to stitch the drone imagery together. Our univariate forecast outperformed the multivariate forecast. I am recommending LSTM over ARIMA because ARIMA, despite better performance, produced a relatively flat forecast. A higher computational wavelet transformation appeared unnecessary. And my study report supports the results from Zhao et al. That single parameter chlorophyll probes can be used for univariate forecasting of chlorophyll in Minnesota lakes. In the future, I'd like to test other machine learning models like artificial neural networks and convolutional neural networks. Using a univariate forecast could substantially reduce the cost of monitoring. Instead of a $10,000 sonde, a single chlorophyll probe plus a do-it-yourself mayfly data logger would cost around $2,000. I'd like to acknowledge the MSU Geography Department, my advisor and committee, Owen Lott and Bryce Hoppy, the MSU Water Resources Center, Bass Lake Association, Dr. Dan Vandermeerwe, and this was funded by an MSU graduate research grant. Any questions?
Yep, so thank you, Ben. So we'll take the questions. So attendees, I believe you cannot speak. So in that case, you could maybe write your question on Q&A or chat box. So then we will read and ask it. Then Ben, could you exit out your the PowerPoint?
Yep. Sorry.
So Ben, did you get to keep any of that equipment?
No, unfortunately, the drone is a Water Resources Center drone.
Are you using it in other projects? Just curious if you, I know you said you graduated, so are they going to continue that research and do more comparison, or is this something that you're going to continue with professionally?
This is something that the university and the WRC could continue. We actually own a Tetracam camera which has 6 bands, so that could be used, and narrow bands could be used to measure NDCI. We've been collaborating with Dr. Bryce Hoppy in the geology department, and Owen Lott has been testing that drone. And so I think this work should continue in the future, but by someone else.
Okay, Kathy, is it my turn? So Ben, I see that your NDVI is outperforming. So in that particular case, can we just use the Centera's camera because it has the near infrared and red, because we just need those 2 bands, right? So do we need anything else? Because one of the objective is to reduce the cost.
That's true. You would only need the Centera's camera, and I have not looked into whether it's possible to purchase a Phantom drone without the camera which comes with it. But or if there's a cheaper drone that you could attach if there's a cheaper setup just using the Centera camera, that would be possible.
Because our objective is to just measure NDVI, and then if that's the case, then when we are talking about NDVI is better, is there a quantified information like what is the difference between the performance of this method versus that method, like how better it is?
I was comparing accuracy based on R², using the data from individual flights. It varied which was more accurate based on the R². When I say that NDVI is performing better, I'm talking about the R² from combining the data from all 4 flights together, and the fact that there was no longer a correlation between VWRI and chlorophyll A. That may suggest that the regression relationship shifts from day to day. So that's what I mean when it's more accurate. It did also appear that there's definitely more extreme values at times with the VWRI and more spatial variability, but I didn't quantify that. I think that would be something that I should look into in the future.
Okay.
So sounds like there is no other question. So let me take just one. So for your future study, you say you wanted to adopt some neural network, machine learning. So what's the benefit for that one?
I think that based on the results that I currently have, the machine learning approach, the LSTM, performed well. The ARIMA forecast, the non-machine learning approach, performed better, but it produced a relatively flat forecast. So I think that the benefit of a machine learning approach, at least currently, appears that it's producing a more realistic forecast. However, there are many other machine learning models that I could try. And if I work to improve selecting hyperparameters, that may improve model performance. So my goal is to see if another machine learning model performs better and to try to improve the performance of the model.
Okay, sounds good. Good, thanks, Ben. I think time is limited, so we'll
Thanks
go
for
for
listening.
the second presenter, Ethan.
All right, I'm back again. So our second presenter is Dan Hamalainen. Did I pronounce that right, Dan?
That's good enough, yeah.
Cool. He went to St. Mary's University. So Dan currently works for Avari GIS Consulting, Inc., which is based out in San Diego, California, as a junior GIS analyst. The company provides GIS solutions to organizations of various sizes in the private, nonprofit, and government sectors. His professional interests include urban and regional planning, as well as system architecture, machine learning, and analytics. And then in his free time, Dan likes to bike, bake, and then read philosophy. And the title of his paper is Validation of a Machine Learning-Based Vehicle Trajectory Prediction Model with Improved Data and Data Management. Take it away, Dan.
Thank you, Ethan. All right. So with autonomous vehicle technology progressing to the point where it seems like their adoption is essentially inevitable, right? We all think that they're going to come eventually. We're just wondering when and how it's going to work. We also started to realize their benefits, and it's become almost public knowledge now. Many are looking forward to the safety and efficiency improvements that they will bring simply by taking out human error off the roads, let alone what they will be capable of when they properly coordinate with other autonomous vehicles. However, until they can become universally adopted, autonomous vehicles are going to have to deal with the idiocy of human driving behavior that we all love to hate. And before governments deem them safe enough to use on the road, they will need to prove that they can efficiently operate alongside conventionally driven vehicles, or CVs, before they allow so. One strategy for AVs to do this task is to effectively predict the behavior of nearby conventionally driven vehicles. If given the local history of all nearby vehicles, AVs could potentially foresee any likely danger and much more by predicting the future paths of neighboring vehicles. So how could this happen? How can this, even be implemented? Well, numerous studies have proposed several different models to achieve such ends. Specifically, artificial neural networks that attempt to predict the driving path or trajectory of human-driven vehicles. In 2018, Nachiketa Dio and Mohan Trivedi of the University of California, San Diego proposed such a model that outperformed the vast majority of its peers. Their model utilizes a specific kind of neural network called long short-term memory in conjunction with a novel convolutional social pooling network. So I'm just going to go over, some of the basics on, artificial neural networks. So with any model, you have an input and then you have an output, right? Whether it be trying to predict something or, even just transform it to achieve some sort of end. Any model is going to have an input then an output. However, with an artificial neural network, instead of just having a few mathematical functions or linear regressions, you're going to have plenty of them, and they're going to be interconnected in ways that might not make any sense, but you're kind of just sort of trying and stabbing in the dark and seeing if it can work. So how do you get these models to work? Well, you give them thousands and thousands of different training samples where you already know the answer to what you want the model to come out with. And as you give it this, it'll adjust the weights of its model within its mathematical formulas and linear regression models and whatnot, to more accurately predict the proper output. So you give it, some sort of input, it tries to predict what the output should be, you give it the output, it then can figure out, based upon, certain training parameters, how to properly adjust the weights of its model so it can better predict future inputs or predict future outputs with different inputs. So you just keep running these inputs over and over. You see how it's going. You might change like a few things here and there, and then you keep going with that. And then once you find that you've trained your model to its fullest, you then test it with a different set of data that it hasn't seen, but in a similar format, obviously, to see how well the model performed overall. So the study that I'm basing my study on leverages a certain kind of neural network called long short-term memory, or LSTM, which sounds sort of like a weird redundancy, but basically what it does is, instead of just being inputs then outputs, if you have a sequence of inputs that are, along a series of times, so like at 1 second, at 2 seconds, at 3 seconds, you can input each of these, whatever these inputs may be at each second. And as it processes each input, it'll sort of keep a memory of what the previous input was and how it went about that. And it will try to connect sort of the relationship between these different inputs as they come in the time series. So it's super useful for things like natural language processing and for driving, because, driving is a series of interconnected steps where one position at time t is super dependent upon the time prior, and the next time, or the next position at time t+1 is going to be incredibly dependent upon time t. Another aspect to Dio and Trivedi's model is something called a convolutional social pooling network. I'm not going to get too bogged down in the details of this, but essentially, in order for their traffic prediction model to work its best, they need to take into account the context that a vehicle is driving in. In other words, if it's trying to predict the red vehicle and where it's going to go based upon, 3 seconds of its driving history, it needs to take into account the three seconds of history of the neighboring vehicles, right? And how they do this is by creating a neighbor grid where at each time step in the data for this red vehicle, we have a 13:3 grid where each of the 13 slots in each of the adjacent lanes and its own lane represent about 4.93 meters of space, which is about the size of a standard vehicle. So, and then where the convolutional social pooling aspect comes into place is, because not every single traffic scenario is going to match up with this, as we can see here. It's, it doesn't want to necessarily memorize each and every single traffic scenario it's come into contact with. So it sort of distorts it and blurs it so it can kind of get a general idea and memory of how things operate, without getting too bogged down in the specifics of the specific traffic scenarios it's been presented with. So for this model, the inputs are for each 1/5 of a second across 3 seconds. We have the X and Y coordinates of the vehicle in question, along with its lane maneuvers, which is just a matter of changing lanes over the course of this time frame. Its braking maneuvers, which is just significant deceleration or not, as well as the coordinates and over this time series of its neighboring vehicles, their lane and braking maneuvers as well too. And what the model outputs is for each 1/5 of a second across 5 seconds, we have the X and Y positions, as well as the lane and braking maneuvers across these 5 time steps. So in order to train, like I said earlier, any sort of neural network, you're going to need a massive amount of data to do it with machine learning. It's the only way that these sort of ad hoc attempts can sort of properly calibrate. And unfortunately, there really aren't many readily available traffic data sets. There are plenty of specific vehicles, but standalone vehicles don't really do much. We want to see the traffic context as a whole. However, a really big advancement came in 2007 when the Federal Highway Administration released their next generation simulation, or NinJSim data set. It contains the trajectories from thousands of vehicles from numerous roads across the US, including Interstate 80 in Oakland and US Highway 101 in Los Angeles during their peak traffic conditions. Each of these data sets features data collected over the course of 1 hour, and combined the two contain 8,665,320 vehicle positions taken every 10th of a second from 11,779 vehicles. And Dio and Trivedi used this exact data to train and evaluate their model. So I'm just going to give a brief little, here's a little screenshot of Interstate 80 in Oakland. The red bounding box is the study area. You can see it features an on-ramp and then the beginning of an off-ramp. And then there's a similar traffic scenario in Los Angeles that they feature on US Highway 101, where you have this on-off ramp contained in the data set or in the study area. So though NinJSim was a major advancement, it utilizes image processing software from 2005, which was a time when such technology was in its infancy. Because of this, numerous studies have found strange behavior that casts doubt on the reliability of the data. The most glaring issue was pointed out by Ben Koifman and Liz He Lee, who found that 13% of vehicles from the Interstate 80 dataset alone overrun their vehicle in front of them at least once during their drive through the study area, which basically means they crashed with their vehicle. So for 13% of vehicles to come into the study within an hour span to get into a crash would be really newsworthy of an incident. Furthermore, the traffic behavior doesn't really change after any of these crashes. So it's most likely that these positions are slightly erroneous and there's issues with noise and whatnot. They also found an exceptional number of vehicles with infeasible acceleration, which are values over 3.05 meters per second squared, along with low constant speeds for long periods of time, over 5 seconds. And these indicate that the trajectories are likely erroneous, yet because it was the only available, many traffic studies still utilize the NinJSim data. Fortunately, though, researchers Robert Kajowski, Julian Bach, Laurent Klaker, Bastian Lampe, and Lutz Eckstein released their HiD dataset in 2018. It features 60 sets of data from 6 German freeways, each of which includes both directions of travel. It comes in a very similar format to NinJSim, but it leverages newer image processing algorithms from the past decade. It is also similarly robust in that it features 15,890,283 positions, 10 per second, from 110,516 vehicles. And this presents an opportunity to train and evaluate traffic prediction models with a potentially improved data set. So the purpose of this study was to train and evaluate Dio and Trivedi's 2018 model with both the NinJSim and HiD data sets, then compare the results. And this includes confirming the errors found in the NinJSim data set and check for errors in the HiD data set, prepare the data for the model, confirm that the replicated model has similar results to the original study when using the NinJSim data, and then train and evaluate with the high-D data set. So I wanted to confirm that the Ninsham data set did indeed contain these errors. So, and I found that 1,238 vehicles, about just over 10%, from both Interstate 80 and US Highway 101 overtake their lead vehicle, but behave as if no crash had occurred at all. Furthermore, nearly all vehicles feature abnormally high acceleration, values over 3.05 meters per second at some point in their trajectory. And then 3.30% of vehicles feature low constant velocities at or below 1.52 meters per second or 3.4 miles per hour for 5 seconds or more. And this is indication of an error because in stop and go traffic, you're not going to be maintaining for 5 seconds that low of a speed. Sure, it's common for you to be going 60 miles per hour for minutes at a time because you can use adaptive cruise control or even just be good with your accelerator. But for you to be going such speeds for 5 seconds or more in stop and go traffic wouldn't make a ton of sense. So then I checked for the high-D data set for errors, and 3 of the 60 subsets feature vehicles traveling backwards. This error occurs only in instances of stop and go traffic though, which probably means that the image processing algorithm fails when presented with such behavior. Luckily, this can be fixed by just omitting those 3 subsets. That's one of the advantages of this data set is how partitioned it is already. And another error I found was that vehicles begin their trajectories at various starting positions on a given road, which is an error because drivers likely did not fly their cars into the middle of the road, whereas other drivers drove into view conventionally. And this is an issue for us because it results in missing neighbors. So because this vehicle randomly appears out of nowhere, we're missing its beginning of its trajectory, which means the vehicles that it was neighboring, we're missing the original vehicle in question to be a neighbor for any given vehicle we want to analyze. So we can't look at its history for that section. So I implemented a solution or an attempt at a solution and to this inconsistent start problem, and it was to create a standardized start position or cutoff, and that gets rid of the majority of the irregular starting positions. It sort of standardizes it. Yet still, there are vehicles that go beyond the standardized cutoff. So in order to deal with those, I predicted the time it took for the vehicle in question to get from the cutoff to its fake starting position, with the idea being to use this time duration to filter out positions of would-be neighbors so the model does not use them as samples to train or evaluate the model. So to get into the specifics of this, a linear model is created to predict the amount of time it took for the vehicle to get from the start of the study area, X start, to the fake starting position, XI, based on the vehicle's velocity at XI. And this model is created by running a linear regression on the amount of time it took for other vehicles to get from the start position to XI and their velocities at XI. So we're basically using the correlation between time it took to get there with the velocity at that position. And positions of vehicles that would have been neighbors with the vehicle's missing positions are then filtered out. So anyone that could have potentially been a neighbor of this missing path, they're gone because we don't want to deal with it because we don't have their proper traffic context. So then beyond remedying the errors in the high-D data set, the data, we then go to pre-processing the Ninsham data set, and in its original format, it contains X and Y coordinates, timestamps, and lanes for each position, for each vehicle. The model requires all of these along with encodings for lane and braking maneuvers, as well as a quick way to access vehicle IDs for neighboring vehicles. And this is based all off of Dio and Trivedi's pre-processing steps. Just want to get into these lane maneuvers quick. Basically, that's just changing lanes. You go from left to right. If you don't, you're staying in your lane. And then for the braking maneuver, if you decelerate enough, it's considered a braking maneuver. If you don't, there's no braking maneuver. And you can change lanes and brake at the same time. If they're separate maneuvers, you can have both. So then for high-D, some additional pre-processing, as well as those outlined earlier, were required. Vehicle positions were translated from the corners of the vehicle to their centers. This was done because I found that a lot of the vehicles were changing lanes and changing back quickly. And that's probably because their position is close to the edge of is on the edge of the vehicle, meaning if it swerves at all within the lane, it might be registered as a lane change. And then
Dan, got about 3 minutes left.
sorry, okay, thanks. And then travel direction is made consistent by flipping one direction to match the direction of the others or reflections. So the machine learning cycle, I'm just going to go over this really quickly. You train, like I said earlier, and then you might implement a validation step. And the validation step is sort of like, how are we doing? What can we do to improve this training cycle? Cool. And then finally, once you feel good about all that, you go and evaluate the model with a final set. But the important part of this is that each of these requires their own separate data sets. You can't mix and match, otherwise you're basically cheating on a test. So Dio and Trivedi, they just partition by time. So they split up the data set. The first vehicles are in the training, the next set are in the validate, the final are in the evaluate. The problem with this is it biases because you're biasing towards certain times. You also have the issue of possibly severing from your neighbor, so you're missing proper traffic context. And with the high D data set, partitioning is a lot easier because you can just go subset to subset to different partitions. The criteria for finding the best possible partition was trying to keep a 4:1 size ratio of number of samples. Exposure to each of the 6 locations is at least once, and to try to maintain similar macroscopic traffic properties, specifically average traffic flow. So then once running this, I implemented this in Python using a library called PyTorch to sort of, and that's what Dio and Trivedi did, trying to replicate their study. And so using the NinSim data, I got similar results, slightly lower errors, but who knows what that's due to. And then the NinSim versus the high D data set, the high D behaves significantly better. Error is measured in root mean square error, so it's the distance from the actual position to the predicted position. What is that distance? That's the error, and we're summing that and averaging it for each vehicle. The high D data sets behaves or operates significantly better than the NinSim, with the exception of the 5th time step or the 5th second. The error jumps inordinately at that time step.
1 minute.
1 minute, you said?
Yep.
Okay. A possible explanation for this might be due to the variability in the different speeds and velocities between the data sets. The NinSim data set really only features data from rush hour traffic, so it's pretty stop and go. There's some that go, a little bit faster, but they're few and far between. Whereas the high D data set, it features lots of different speeds. So that variability might be affecting that, because that 5th time step, someone could be going so much faster than the rest of the vehicles that it could be really skewing the error for a few vehicles that are just going really, really fast or randomly accelerating towards the end of their trajectory. However, you'd sort of expect more of a linear relationship in the change in error. So you see here that we sort of have this hockey stick graph where it just jumps up in error really quickly. And you wouldn't expect that given this sort of relationship necessarily. Okay, so I'd like to give a special thanks to Professors John Ebert and Greta Poser and the rest of St. Mary's University of Minnesota, Woo Suk Jang and the rest of the Minnesota GIS LIS Consortium for setting this up, and Sarah Ewald and the Ewald Consulting Company for helping to set all this up. Thank you, and any questions?
Yeah, we'll take the questions. So, and then Dan, could you exit out your PowerPoint?
Catherine, is this my turn to start?
Go ahead.
Dan, good job. So now I have a question in your neural network. Is there a specific reason when you have T0, where you have X and Y, your Y is connecting to 4 nodes and X is connecting to only 2 nodes? Is it
So with
specific,
that,
or you just made that graphics like that?
yeah, that was just I just created using a chart software, just as an example of a neural network, just to sort of give people an idea of what it kind of looks like. That's pretty much it. That might not be a very rational neural network by any means. So yeah, it just sort of was connecting nodes, to give an example.
Okay, so it should technically connect to all the nodes
Yeah.
from the input layer, right? Okay.
Yes. In the actual model, they everything is interconnected from the input to output. Yes, correct.
And you had two hidden layers there of nodes. Do you know if these models that were used, how many hidden layers of nodes they had?
So the amount of layers used, it's quite a bit. Their paper outlines it. There's also a GitHub repository that you can check out. That is pretty useful. There's plenty of really good comments on it, especially. Just go to, I think it's on Nachiket Dio's GitHub repository. The comments there were incredibly helpful. It seemed like other people were helping them out as well. And it's a really interesting look through at a model like this. It's fascinating. So you get a full detailed look there, but there are plenty of different, activation functions, and essentially the main component though, in terms of the actual neural network, is an LSTM encoder for the inputs, as well as a decoder for the output of the 5 seconds. So that's sort of the main component. And those LSTM encoders and decoders are used for both the vehicle you're trying to predict the trajectory for, as well as the traffic context. So an LSTM encoder is used that goes to the convolutional social pooling network. And then that is decoded out to help concatenate with the output for the LSTM encoder decoder for the vehicle you're trying to predict the trajectory for. So that's how it adds in the context. Each of those vehicles, neighboring vehicles, they get their own LSTM encoder. They all get pooled together. Then that pooling is decoded out to give the traffic context to the trajectory prediction.
Good.
Is that good, Rama?
Yeah, I'm good. You can go ahead.
Those are good questions. I want to give you the opportunity, Dan, in your paper, you kind of leave off a little bit more of a philosophical kind of approach to this. And, 90% of any spatial project really is data management, understanding it. And you've done a really, interesting project here with 2 different data sets in 2 different parts of the world, right? But also, what's your perspective on the future of this type of collection? You kind of lead in your paper a discussion about how we all have it in our phone and we do it voluntarily. And in order to make UVs, standardized or to make them safe for highway use, what kind of restrictions or what kind of laws or rules must they follow in order for that machine learning to be predictive? And you talk about how the best monitoring would be in vehicle. And a lot of these data sets are taken from aerial, photography. So some sort of bridge between those 2 things are happening naturally, I think. Just because I use my phone, right, for direction, and I'm being collected and I kind of volunteer that information, but I think it's for my own use. So I just want to give you an opportunity to expand on that, because I thought that was a pretty interesting thing in your paper that you didn't present.
Yeah, sure. It's a good question. Yeah, so one of the things I touched on in the paper is, where do we go from here? I'm mainly focused on the fact that we need better data to figure this out if we want prediction models to work like this. But it does lead into an ethical question, though, in terms of, we want these vehicles to effectively behave. There is sort of a compromise between privacy and efficacy in the sense that if we want to collect all this data to help advance this technology, we kind of need to give our coordinates out and our driving behaviors out in public, so that way people can research it. And when we do have autonomous vehicles actually on the road, one means of them sort of coordinating and with conventionally driven vehicles is knowing your positions, over the course of the past 3 seconds, 5 seconds, whatever it may be. So that way we can properly, or the AVs can properly predict what you're going to do next. So that way they can avoid any potential danger and be more safe. So there's that trade-off. And that even leads into, well, if you want to be super effective, You can maybe keep a driving behavior history log where you have all the trajectories for all your past drives, with the intention being, we know your driving behavior and we know sort of how to navigate around you as a driver, which to some people might be very against that. But that's the compromise. Do you want privacy or do you want efficacy in this sort of regard? And I don't know if there's a bridge. Hopefully there is a bridge between those two, and we don't have
Maybe offering 10% off of your car insurance with your
Exactly.
teenage drivers.
Yep, that would make complete sense. Yes.
Yeah. All right.
It
Well,
might be.
good. Thank you.
Thank you.
Thanks. Interesting.
Any,
Wu,
yeah,
before you begin, the 5 minutes is up, but if you want to ask a question, then
so is there any like a question from our audience? No? So let me ask the one question, So sounds like the limitation of the paper is that it rely on a vehicle track to assume the maneuver class and a future trajectory. So what kind of like a complementary information can be improved these types of like accuracy for future motion prediction?
Yeah, great question. So none of the data that I used is actually validated by having like a GPS sensor or GPS tracking on the vehicles and actually seeing if the image processing works. So they don't ever, at least they don't make available any sort of validation like that in both the NinSim research paper and the HID research paper. So anything like that where you actually are, all right, we have a recording, cool, we track the vehicles. Now let's see if our tracking actually worked by comparing it to the real GPS coordinates. That would be incredibly helpful, that alone. And it would be super interesting because, I don't know, image processing is really cool and we want to get that improved too. So.
Okay, thank you. So
Thank you.
it's almost like 12. So thanks, Dan. And then Ida for the third presenter.
alrighty. Well, thank you, Dan. Our third presenter is Lucas Rosen from University of Minnesota. Lucas received his Bachelor's of Science degree at the University of Wisconsin River Falls in conservation. Later, he started a professional master's in geographic information sciences at the University of Minnesota, Twin Cities, beginning in the fall of 2019. His focus has been applying GIS to environmental sciences and natural resources. And then over the last couple of summers, he's assisted in showing spatial data for potato fields, which is what the project he is showing. He's created historical maps for the Minnesota townships, as well as modeled some climate maps for Toro. He is involved in genetics, environment management, socioeconomic GEMS, which is an organization that views agricultural issues spatially and temporally. His goal is to use modeling in GIS to solve agricultural and environmental problems. And the title for his project is Using Spatial Autocorrelation to Measure Soil Health in Potato Fields. Lucas, good luck.
Okay, just a moment. All right, hello everyone. I'm Lucas Rosen and my project is using spatial autocorrelation to measure soil health in potato fields. This study was funded by the National Institute of Food and Agriculture, or NIFA. Carl Rosen and Linda Kinkel are the PIs for the project and generously provided me the data to assist them to making maps on potato fields for soil health. Specifically, they wanted me to focus on objective 2 for this long-term study, to determine on-farm soil health-based indicators associated with potato crop health, yield, and quality. Why do this study in the first place? Worldwide, potatoes are the third most important crop used for human consumption and a $4 billion industry in the United States. Soil-borne pathogens, such as verticillium, can account for half of all crop loss. While traditional soil sampling methods measure nutrients, physical characteristics, the biological components of soil health have often been underutilized or ignored in field studies. So what is soil health? The Natural Resources Conservation Services, or NRCS, defines soil health as the continued capacity of soil to function as a vital living ecosystem that sustains plants, animals, and humans. Biological factors include the symbiotic relationships between the microbiome and plant roots, as well as the pathogens. Physicochemical factors include the physical properties of soils, such as soil structure and texture, as well as the chemical properties, such as the macronutrients. Both biological and physicochemical properties are impacted by human management, including crop rotation, tillage, irrigation, use of cover crops, and fertilizer use. Why look at this spatially? It's because soils vary over space and time. Physical properties in soils, such as compaction and erosion, can change over time by tillage decisions. The chemistry of the soil, such as the macronutrients, changes spatially and temporally based on user input as well as plant uptake, leaching, and runoff. As you can see in these fields, this is the same field, but it varies both in elevation, this DEM, as well as the soil type found in this soil survey. So the goal of this project is to perform an exploratory spatial data analysis on potato field soil health indicators and compare the performance of 3 different interpolation methods. I will first go over the study area and then go over how the samples for soil health indicators were collected. Then I will go over the spatial methods of how they were analyzed before finally going over the results. This study area was done in the sandy plains of Minnesota. 3 fields were selected for a long-term study beginning in 2019 and divided in 14-acre subsections. All fields had a sandy texture with low nutrient capacity, and they all had conventional practices, including irrigation and fertilizer. Fields 1 and 2 are located in Sherburne County. Field 1 on the right has been cultivated on for over 40 years. Field 2 on the left has just started cultivation. It used to be fields and brush. One hypothesis was that field 2 would have lower pathogens because it hasn't been farmed on, and thus a higher yield. Field 3 is located in Benton County. Note that different agricultural practices were used in field 3 than fields 1 and 2. So how were the soil samples collected? Well, a gridded scheme was used to collect 20 soil samples based on previous studies. They were collected 2 times during the year, both in the spring before planting, as well as summer, approximately 60 days after planting. The GPS coordinates were recorded at the sample points. What indicators are we looking at? While the microbiome itself wasn't measured in this study, there are biological indicators that show the response of the microbiome. Organic matter is part of the soil that contains carbon. Permanganate oxidizable carbon is the part of organic matter that can easily be taken up by microorganisms. Soil respiration is the amount of carbon dioxide that's exhaled from the microbiome as well as plant roots and is measured using the Solvita test. Other biological indicators included the diseases verticillium, which is a soil-borne fungus that causes potato early die, or PED, as well as potato scab, which infects the tuber and is caused by a bacteria. The chemical indicators measured in this study were macronutrients, specifically phosphorus, potassium, and nitrogen. Phosphorus was measured using the Bray extraction method. Potassium was measured using the ammonium acetate method, and nitrogen, specifically the nitrate N, was measured using the potassium chloride extraction. Total yield was also measured in this study. The spatial methods I used to analyze the soil health indicators were Moran's eye and interpolation. Moran's eye measures the soil autocorrelation contiguity as a coefficient. It really just measures how similar the neighboring points are to itself. A value of 1 indicates perfect contiguity, meaning that the two values are similar to each other. A value of -1 indicates that they are repelled by contiguity. The value next to it would be different than itself. Finally, a value of 0 indicates spatial randomness, so you can't really predict what the value is. This is all measured using a Queen's matrix, which uses the edges and vertices to determine weights. The interpolation methods used were inverse distance weighting, IDW, ordinary Kriging, or OK, and empirical Bayesian Kriging. Inverse distance weighting is deterministic and just uses known values to predict unsampled values. Ordinary Kriging and empirical Bayesian Kriging are geostatistical methods, which means that they predict error in the known values and try to compensate, in this case, using a semi-variogram. IDW and ordinary Kriging have often been used in previous studies. The reason why I also chose empirical Bayesian Kriging is because that's what Esri was pushing for during the time of the study. To calculate Moran's eye, a Queen's contiguity matrix was created in Geoda and uploaded to a Jupyter Notebooks. The GeoPandas Python package was used to upload the shapefiles. Finally, the PySolve package used the Moran's eye function and input the soil health indicator, as well as the Queen's matrix to output the average Moran's eye for a given field. To measure interpolation, Model Builder was used in ArcGIS Pro. The extent and the mask was used as the field boundary to clip it to just the boundary of the field of that trapezoid. And then the input data was used to output the interpolation method as a raster data set. Note that different parameters were used for each interpolation method. To do a statistical analysis, the p-value was used to determine the significance of the null hypothesis for Moran's eye. A p-value less than 0.05 is considered statistically valid. To determine the statistical significance of the interpolation methods, a cross-validation or leave one out was used to compare the predicted value to the sample value. The output shows a root mean square error, or RMSE. The lower value, the better, but it is skill specific. I forgot to mention that a non-spatial method used was a linear regression model, which compared the total yield to each soil health parameter. That was statistically measured using the R squared. And R squared greater than 0.7 is considered statistically valid. While I was hoping to see statistically significant results in the spatial variation of the field, that unfortunately wasn't the case. There was little spatial autocorrelation. The Moran's eye was near 0, and the p-values were less than greater than 0.05. This indicated spatial randomness and that the null hypothesis could not be rejected. For the interpolation methods, there was a similar RMSE across all methods, meaning that no one was greater than the other, and the RMSE values were all high, indicating that the maps were probably not accurate. For the linear regression models, there were weak relationships with the biological indicators. The R squared was near 0. There were some significant chemical relationships with a maximum R squared being around 0.8. Here are the results of the Moran's eye. They show both the average Moran's eye value as well as the p-value. I would highlight areas of significance, but unfortunately, none were found in this study. This map, or this table, shows the all interpolation maps for the total yield for each field. While the interpolation methods do show spatial variation, the RMSE values are high, meaning that they're probably not accurate. Overall, EBK had the lowest RMSE, but some of the EBK maps look incorrect. For example, I know that field 2 had the lowest total yield in the center, but the EBK does not reflect that. This shows one linear regression model for the biological soil health indicator. Overall, organic matter had the strongest correlation, though still pretty weak at R squared of 0.2. It's surprising that organic matter had a negative correlation with total yield, but field 2 did have the highest organic matter and the lowest total yield. For the linear regression models, for the chemical soil health indicators, overall, phosphorus and potassium had the strongest correlation with total yield. It's surprising that phosphorus had a negative correlation with total yield because you would think that more fertilizer is better. But it could mean that the fields are over-fertilized. It is predicted that potassium would have a positive correlation with total yield, as we see here, though it isn't statistically as strong as phosphorus. So when I first started this project, I thought that I would find strong spatial patterns with spatial autocorrelation and interpolation. But unfortunately, that wasn't the case. There was no strong spatial correlation found in this study. This could be due to the complexities of soil and that a single parameter might not be appropriate to model spatially. Furthermore, the microbiome was not measured in this study. Measuring the microbiome could help explain some of the biological indicators. Another point is that my study was just a small part of one season in a long-term study. Further research could show relationships with yield that I didn't detect. Determining spatial relationships can help avoid unnecessary resources, increase yield, and reduce environmental degradation. Once again, this study was funded by the National Institute of Food and Agriculture, or NIFA, in conjunction with the United States Department of Agriculture. I would like to thank Carl Rosen and Linda Kinkle for providing the data, as well as Brian Runk for assisting me in the project. Thank you, and any questions?
Yeah, so we'll take the question.
Catherine,
Nice
you
job,
want to
Luke.
go?
Sure. Thanks, Rama. Nice job, Lucas. Thank you for sharing that paper with us today. I have a question with the tools that you use, the Kriging and the IDW. I'm trying to find it. I think you said it, but did you adjust and account for the search radius and the scale of the field that you're looking at, since they were very similar in size, and just adjusting some of those search radii?
Let's see if I can find it. I just used the standard search radius, which was, I think, 12 for each method.
I'm just wondering, sometimes using those tools, my perspective anyway, which is kind of light, is it's very video game-ish like, where you can adjust those and change them and see if, you know, what that search radius might be. I noticed on some of the maps that were generated, you kind of have, you know, a ring around the rosy out of each sample site. And so that kind of, you know, also doesn't give very visual results. So adjusting that or looking at that or thinking about those inputs is one way to, probably wouldn't have changed your outcome, especially with the linear regression that you had for the yields. But, you know, maybe there would have been something there to adjust anyway. So thank you.
Yeah, possibly. Yeah, when you ever get those ring around the rosies and the interpolation, that means that the spatial variation is extremely localized, which is not what we want to see in a field.
Right. Yeah. I think you're kind of limited too by the size of the field that you had. And, you know, you had those two neighboring fields, maybe that study area for the whole, you know, just going outside of it and looking a little bit broader might have been something to compare to as well. I don't know, that's the first thing I would want to do.
Yeah, definitely. And yeah,
Yeah.
and 20 points is kind of really
Yep.
low to do interpolation. Ideally, we would have had more points, but it was also kind of the practicality of how many samples we can collect. And the reason why it was gridded was because there was no known zonal patterns in the field.
Right. All right, thank you.
Okay, Lucas, you kind of addressed like, you know, 20 points in a particular field, and we are doing statistical analysis when we collect samples, should be at least 30 or more. preferably if we have 100, if we could somehow increase the number of sample points, that might give a better result with changing the parameters in those. But I have a little bit different question. I saw one of your model, which was Moransai. It seemed like it's an R2 model. And at the same time, you mentioned that you use Geoda, Paisal, and I think in your paper you have mentioned Anaconda. Is there a reason why you are using so many different open source art type of software? I think all these things can be done in
Sure, yeah.
ArcGIS
So
itself, right?
yeah, and I actually did it in ArcGIS well, and it had a similar Moran's eye, like it was off by 0.01, which is practically the same. The reason why I did the open source was because I could kind of see how they calculated the Moran's eye. And the reason why I used Geoda to create the matrix was so I could visually see the matrix, because you can do just a Queen's matrix in PySal, but you don't really know if it's correct. And especially with points, you want to make sure that the edges connect and diagonals connect.
Okay. So we are basically trying to at the same time compare different applications to see how they're coming up with the same results in algorithm. Yeah, there is one challenge when we try to do if we use say certain tools in ArcGIS and then we move to Geoda and try to compare. That comparison can be at 0.01 level, so it can be different.
Right. Yeah, and I was thinking about using ArcGIS, but I couldn't really tell what they were doing.
Okay.
It gave me a result, but
Okay, good. Thank you.
Okay, sounds like we don't have any question left. So thank you, Lucas. So it's our last presenter.
Alrighty. So our last presenter is Patrick Kalonde. I hope I said that right, Patrick. He went to St. Cloud University. He is a Fulbright scholar at St. Cloud, pursuing a master's degree in geography, specifically geographical information sciences. He has a background in environmental sciences and is interested in exploring innovative application of frontier technologies, such as drones, Earth observation satellites, and machine learning in public health and environmental protection. He's previously attended a 12-month internship with Malawi Liverpool Wellcome Trust, a leading clinical research institution in Southern Africa. And while he was down there, he got exposed to research trends in vector biology and malaria epidemiology and published a paper in Malaria Journal. His research thesis at St. Cloud is focusing on the use of drone technology and mapping plastics, particularly in a semi-urban environment. He is also a recipient of the Young African Leadership, or YALI, and he volunteers to develop capacity of his home community, which is in Malawi, Africa, in managing existing environmental and social challenges. And the title for his project is Modeling the Ecological Niche of Anopheles funestus mosquitoes across Africa using Wallace package. And here you go, Patrick.
Thank you very much for a very nice introduction, the moderator. My name is Patrick Kalonde, and this afternoon I'll be presenting to you one of the projects that I did at St. Cloud State University as part of a final project for one particular course. So I come from the Republic of Malawi. This is a country widely known to be the warm heart of Africa, very small in Southeast Africa. And as mentioned by the moderator, a few years ago, I participated in an internship where one day I was attending a meeting and I saw this graph, which you can see on the right-hand side. So this graph is about malaria, which is according to the Center for Disease Control, CDC, malaria is a serious disease that is caused by Plasmodium. So Plasmodium is a parasite that infects certain types of mosquitoes that feed on humans. And this graph highlights that despite much progress over the past 20 years, the efforts in reducing malaria has stopped reducing the disease burden. As you can see, like towards from 2015 up to the like the past few years, the graph is almost flat. So as a result now, we have about 200 million cases of malaria every year. And approximately, we have about 400,000 deaths from malaria alone. That's according to WHO. And many of the people who die from malaria, they come from one region, which is sub-Saharan Africa. And malaria now remains to be a #1 killer of under 5 children. So most of the children under the age of 5, they don't see their 5th birthday because of this disease, malaria. So the question is, why is the graph of malaria almost flat? Well, according to literature, it is several researchers have pointed out that the graph is flat because the parasite that causes malaria has now developed resistance to the drugs that are administered in the hospital. Other researchers have also come up to point out that it's not only that, it is also because of the mosquitoes that have changed. So there's increased evidence on mosquito resistance to insecticides, but also there's more evidence on change in biting behavior of mosquitoes. So normally what they do, they administer mosquito nets. So mosquitoes have stopped biting, like at night, they're biting at different hours. So that's why mosquitoes, malaria is still further effort. We need to develop new interventions to fight malaria. Not only that, just because the mosquitoes are now actively biting, the burden of other diseases that are transmitted by malaria, by mosquitoes rather, like for example, elephantiasis, even the arboviruses like dengue, the virus that causes Zika, the burden is increasing. Just to give you an insight about the burden, for example, elephantiasis, the disease burden is now about, every year we're having about 51 million cases. Just imagine about that. And the burden of diseases like dengue, it has increased 40 times just in the past 50 years. So it's really interesting to study about mosquitoes. But mind you, what is more interesting is to develop new tools that can help us to effectively manage mosquitoes. So, as I mentioned, this is particularly malaria is transmitted by Anopheles mosquitoes. So about 95% of the malaria cases, they are transmitted by only 6 species of mosquitoes, of which one of the species is Anopheles funestus, which is the main focus of my research. So knowing areas that are suitable for mosquitoes can help public health to identify areas that can be prioritized for public health interventions. And one of the tools that geographers can offer on the table is by developing species distribution maps. So species distribution maps, these are maps that are made by modeling locations where an organism was observed to about environmental factors, for example, temperature, rainfall, humidity, and others. So one of the most commonly used approach is the maxent, like maximum entropy algorithm. Despite wide use, maxent is implementation of maxent is a very subjective process. Selecting of optimal parameters varies from one user to another. One paper actually pointed out that like most of the authors, most of the researchers, they just use default parameters. So there's a package that has been developed in R, ENMVAL, I don't know how to pronounce it correctly. So that package helps researchers to, instead of just implementing it using default parameters, you learn the mark sense. So it creates several different options of parameters. So it learns like maybe so many models, and it presents statistics on the performance of each of the possible parameter combination. Based on that, it helps a user to select one parameter that is like a set of parameters that is appropriate for that particular species that you are modeling. So a team led by CAS, they have built on that package and other packages to build a graphical user interface application within R statistical language that can help people to develop species distribution models. So as part of this project, I implemented that tool to explore the distribution of Anopheles funestus mosquito species across sub-Saharan Africa. So this is what MarkSense does. You take presence data, you model it to environmental variables, and then you come up with a species distribution map. One point that has to be highlighted is about how the algorithm is implemented. The choice of parameters, MarkSense helps one to optimize on the parameters to use, rather by using ENMVAL. So my study area, I focused the sub-Saharan Africa region, the region that is in gray. So this is the region that has been main focus of most of the malaria research. There are maps that have been published on malaria, particularly in Africa, under what they call Malaria Atlas Project, led by the Oxford University. So I tried to model the suitability of this particular region to Anopheles funestus. So that's my study region in a nutshell. So my data sources, I took data on mosquito presence from a researcher from Kenya Medical Research Institute, David Kiaro, and I filtered records from 1970 to 2015. And I took the environmental predictors from WorldCrim. So these are biogrammatic variables with a resolution of 5 kilometers by 5 kilometers. So basically the presence data, it came from a survey like the one that you are seeing on the screen. So that's me in Malawi when I was doing my internship, collecting mosquito larvae for further assessments in the lab. So all the data that David Kiaro reported was collected in a similar way to the one that you are seeing on the screen right here. So basically what happens, just to reiterate what I mentioned previously as the method, I took data from David Kiaro, which are points, just like the one that I was collecting. So these points, like they date back from the 1970s up to now. And then I used each and every point that I collected. I had to extract the, so like I had 19 biogrammatic variables from WorldCrim. So I had to extract its value. And I just wanted to visualize how, like using 3 variables on how like each point can have like different temperature, let's say humidity and precipitation. So using that, I fit the model using R. R did much of the work on my behalf. So yeah, so when I did that, R selected the best, using Wallis package, it selected the best parameter and it produced a species distribution map, which I finalized the preparation using ArcGIS. So the best model had the AUC value of 0.85, and that model is the one that was considered to have the optimal settings, and we predicted the suitability, as you can see on the screen. So as you can see in the southern part of Africa, South Africa, not even suitable, very low suitability. Northern part of Africa, close to Sahara Desert, not suitable, but in the middle of Africa, that's where there are the key variations that we can see. Now, I tried to compare this map with the existing map for Anopheles funestus for Africa, which was published by the Malaria Atlas Project, this one. As you see from the previous map, there are differences. So this map that I'm showing you was published under the Malaria Atlas Project by Professor Sinka of Oxford University. And when I saw the differences, like you see some of the locations that were in a bit red, now they're in green. For example, in the middle, like close to the DRC, it's no longer the, it is showing low suitability. So I was trying to see what can be the source of the differences. So I saw that Professor Sinka, in their research, they used boosted regression tree, which is an approach that incorporate pseudo absence data, where they indicated in the article that a team of experts had to select areas that are not suitable for anopheles phonestas. So there are also studies that have indicated that to some extent, using that approach is subjected to bias from the experts. So I saw that maybe the difference can come from there. But let's go deeper into what, how different are the two maps. So I tried to visualize the difference between my predictions and the predictions from the malaria atlas survey. So in the southern part of Africa, there was a bit like, if you can see like the color, this color, like which is dominant in the southern part, these areas and towards the Sahara Desert, there's much more congruency. My predictions are much more similar to what was predicted by Professor Sinka. But then there are patches of similarities in Madagascar, parts of West Africa, and some little bit parts of Central Africa, some parts of Central Africa. And there are positive differences, particularly in Central and West Africa. And I also observed negative differences particularly in Central and Southeast Africa. So the variations can be, as I mentioned previously, can be explained by differences in the modeling approach that we used. But also beyond that, I noticed that the data which they use is different from the one that I used. I used data from Rift Valley, so they use a different source. So that might also be a source of the differences that we are seeing on our map. Now, in terms of conclusions and limitations, my study has produced a species distribution map for Anopheles phonestas using wireless package. And the map that I produced is slightly different from existing maps. But what is key for my map that I produced, unlike convention Maxent modeling, the selection of parameters for implementation of Maxent this time around was optimized. And Wallace helped me to document the entire workflow such that I can share a code that someone can reproduce exactly the same results that I came up with. So, of course, I saw that using wireless package, there are some shortfalls compared to using the actual Maxent application that people download. Maxent, implementing Maxent using wireless does not give information such as the influence of individual variables like temperature. So it's difficult to know how each individual variable contributed to the overall final model. And I also saw that within Maxent, using wireless, they incorporated like issues to do with like they said, if points are closer to each other, if you are building a model using such points, and you split them to be some to be testing, some to be for training, this closeness can have an effect towards how you like the reliability of your model. So using wireless, they incorporated like spatial thinning where we were removing points that were closer to each other. So I chose 10 kilometers when I was implementing my SDM, but it is a subjective process still. That decision was left to me. If it was a different researcher, a different decision could have been made. So in terms of limitations of my study, I overlooked the influence of using a different data source from what was used in previous research studies. And this made it a little bit difficult for me to explain the variations that I saw between my predictions and those of previous studies. So these are some of the selected references that I used. And I'm very thankful to my research advisor, Professor Korff, my cartography professor, Dr. Togason, and Dr. Michelle Stanton from Liverpool School of Tropical Medicine, who introduced me to vector-borne diseases, and a friend and also a colleague from Liverpool School of Tropical Medicine, Grant Kay, who is a PhD student now. Reaching that far, thank you very much for your wonderful attention. Many for questions.
Okay, thank you, Patrick. So now we'll take the questions. The Patrick, could you exit out your PowerPoint too?
So I see there is a hand raised. You want to take that question? Do you have a question, Lucas? Or
Yeah, I do. So I'm curious what parameters, like I know that they're environmental, but what parameters went into the species distribution model?
Okay, so I used biocrim parameters. So there were about 19 parameters. So this includes like annual mean temperature, the mean diurnal temperature range. There was a temperature seasonality, maximum temperature of the warmest month, the minimum temperature of the coldest month, the mean temperature of the driest quarter of a year, annual precipitation. So there were about a lot of variables, 19 of them.
Okay, thanks.
so, Patrick, it's nice to see, like, how you have your distribution compared. And my understanding from your finding is that both regression tree and your model, they have subjective bias, right? Maybe this one is a little bit less, but both are there. Have you thought of actually comparing, although they are based on two sets of data using two different methods, actually somehow trying to find the accuracy, like quantitative, instead of having a difference image and showing what are the differences between yours and theirs? Any kind of quantitative accuracy assessment based on the locations or based on these parameters, trying to compare the models?
Yeah, I agree 100%. Yeah, I think moving forward, I will try to do that. Of course, like I wanted to explore much in literature on like how can I explain like the variations, and I saw that some research studies, they have also like people who are studying different things, not mosquitoes, they saw things similar to what I saw. But then what these people are doing, they learned several algorithms. They could use Maxent, boosted regression tree, and other algorithms. And then they built an ensemble model at the end. So I think that's also an area which I can extend moving forward.
Okay, I have one other question for the Maxent. You're talking about both space-time data, and you have 19 different variables from the environmental, climatic and others. How do you prepare that data and enter that in Maxent? Do you do like in GIS? Because there is temporal data there also. Like how do you organize that data?
Okay, so starting from particularly I'll focus on presence data that was used. So that guy, David Kialo, the researcher from Kenya, he read like articles that had like published that they observed, let's say, Anopheles funestas. So they had like a lot of like locations of areas where funestas was observed. So it was a CSV file. So what I did, I took that CSV file, I exported it to R and formatted it to fit the requirements of Maxent. So using wireless package, they specified like the data format which they want it to be, like the structure. Say that the first one should be this like the latitude should be the first one, longitude the second one. So I just followed what they recommended. And at GIS, I only used it like I used the ArcMap at the end of everything, like after producing the model, like the map.
So after you got the distribution map, you just brought that into our and made a map.
Yes.
Okay. Thank you.
Not so much a question for you, Patrick. I think, thank you, Rama, for your question. And I just want to give you a little bit of credit. Thank you for pointing out that your own subjectiveness, right, on how you did your spatial thinning and how you went, you're just left as a researcher, you're like, well, this looks good. I'll try this. And then for you to acknowledge that, well, maybe that wasn't, maybe that really is what's skewing my results here. And, I want to look back. What I would have liked to have seen too, and you brought this up as well, a little bit more documented procedure of that model, right? So how you started, where you went through in that process and where you might change a specific part of that process. So you acknowledge that, and I want to give you credit for that. So thank you. And hopefully, you can move on with this research and help make some changes, right?
Yeah.
Yeah. So I hope you continue with this. Disease vectors are a really interesting topic. So keep it up. Thank you.
Okay.
Okay. So sounds like no other question involved, we are very quiet. So thanks to Patrick, okay? So
Thank
I
you.
think this time is almost like, 10 to 1. So I think we need to wrap it up this section. So first of all, thanks for all our four student presenters. You guys did a very good job. And then I really appreciate Catherine and Rama as a judges, and also Ethan as a moderator, and also someone who attended our section. We really appreciate your big support. So enjoy the rest of the day and hopefully see you on another section. So
Good luck, everyone. So do we see how many people were in the session? Did you see how many other folks were joined other than the panelists?
the panel, we have 8, including the student and judges, but we had 5 attendees
Okay, all right.
in this section. I kind of expect a little bit more, but
I saw a few more at various points in
yeah.
terms of other attendees, but yeah, just not too much more, but yeah.
Awesome. And I just want to confirm, Lucas, did we meet each other last night over a projector in the lab
Really.
on campus?
Oh, possibly. Oh, yes.
Okay.
Yeah.
Yep. Okay. Get that all figured out. It was the cable, by the way.
Oh,
It was broken cable. They had to replace the cable.
yeah. Because
Anyway.
it was working when I started. Yeah. So.
Yeah. Good. We got it fixed. Good. Anyway, thank you, Lucas. It's nice to meet you.
Nice to meet you too, officially.
Yeah.
Okay, then see you next time. Bye now.
Yep. I'll be well.